and Vu at Fred Hutch. I actually emphasize Vu's done a lot of the important theoretical work that shows that we can actually do the things we say we're going to do, and so that's quite important. So let's take a look. So first of all, I don't think I need to convince anyone. We all know that Bayesian has become very, very important. It's very important for evolutionary biology. We want to be good at it. And so the important thing, the core of Bayesian statistics is being able to sample phylogenetic trees according to their probability given your sequence data or whatever data you have. You want to sample your trees according to their probability. So in order to do that well, we need to have a good way, we need to be efficient at exploring the space of different phylogenetic trees. So basically the current state of the art is Metropolis Hastings microchain Monte Carlo. And a lot of times this is described as a robot taking a random walk in your space of trees. And that's not very good. It's very slow. And with this is basically leaving us capped that, analysis can't get much bigger than 1,000 taxa because it just becomes much too inefficient. But suppose we gave this robot a pair of skis. So end up with something like this. And so now we need to start thinking physically. So we've got a robot now. A robot's got some position in the space. We're going to call this Q. This is a robot's position. And then its elevation is also equivalent to what we're going to call potential energy. The robot's also got some speed, momentum. And then it's got a kinetic energy which is derived from this momentum. And so if you take the sum of its potential energy and its kinetic energy coming from its speed, then we get what we call the Hamiltonian. So the Hamiltonian is the sum of these two energies. And we got some important things. One of them is that we can describe the motion of the robot through the space. This is just Newton's laws of motion. And the other thing that's important is H is the sum of our two energies. The Hamiltonian is the total energy of a system, and we expect that to be conserved. Okay, so we've got a robot, we've got the space, now we need to give it a few moves. One of them is it just needs to be able to push itself in potentially a random direction. It also needs to be able to move through the space. So just ski, simply letting the Newton's laws of motion take the robot through the space. And the last move we needed to have is it needs to be able to turn around. So I just got some basic flipping move. So now we've got these three moves. And so we've got all these physical ideas, but how do we actually turn a statistical problem into a physics problem? So first of all, we say every location Q, so every location in the space, is actually mapping to a parameter, a set of parameter values for a statistics problem. Then based on this, we say that the elevation is coming from sort of a target density, which is the probability of trees given the data. And so the way we can interpret this is that locations with high elevation have got low probability, and locations with low elevation have got high probability. So I really want to emphasize this because this is backwards to how we usually think about things. Usually you think about hill climbing, you want to get to the top of the hill or your mountain or whatever, because no, it's the other way around. Actually, the high probability spaces are our valleys this time. But this is how we want to construct a physical space, and this is where we want to be using these dynamics and things. And then we need to run the Hamiltonian Monte Carlo algorithm. So how does that look? So the first three steps we've already basically seen. One of them is just choosing a random momentum. This is just giving the robot a push in a random direction. And then we want to simulate its motion. And we can't actually do this exactly. We cannot exactly simulate the motion of a robot through the space, but we can do a simulation which ends up being some sort of approximation. And we do this using something called the leapfrog integrator. It's just a numerical method for simulating the motion of the robot through the space. And then finally, we flip its momentum. Now we have this accept-reject step, and the really important thing is it's using this subtraction of the Hamiltonian from where it started. It's subtracting, the Hamiltonian of the new location from the original Hamiltonian. So the energy is just subtracting a sort of a new energy from the previous energy. Now, if we were doing the simulation exactly, this energy would be conserved. And so ideally, we would accept this acceptance probability to be actually 1. So with probability 1, we'd be accepting our proposed state. But, because it's an approximation, it may not be very good, but ideally, H is going to be approximately conserved, and we can get very high acceptance probabilities. The other thing to emphasize is we've simulated the motion of this robot through the space. It's potentially gone quite a far away, simply by simulating these dynamics, so we're actually maybe very far from where we started, but we've still hopefully got a good probability of accepting this state. So we're going to accept this and reject according to probability A, then we flip back, and then finally we can save this as a sample from my target distribution. And of course, with all microchain algorithms, we want to repeat this forever, or as close as we can get. So why do we even care about, doing something like this? Because simulating physical dynamics is a lot of work. I mean, first of all, we have to sort of know what the slope is of the robot at any position in the space, and that's quite expensive to compute. We already have enough trouble computing what the elevation is because that's just, you know, a posterior probability. Now we also need to know what sort of the slope is of that position. So why should we bother doing any of this? And so there's a nice theorem from Kutz which says, okay, if we've got a statistical space, you know, it's got n variables, n dimensions, then if we make a lot of simplifying assumptions, then the computation time for sort of get an independent sample scales n squared for MCMC, but then for HMC, which we were just looking at, scales n to the 5/4. So this is a big deal, because it means that if we double the number of variables, for example, we double the number of taxa in a phylogenetic tree, then while MCMC would take 4 times longer to sort of get us to an independent state, HMC can take less than 2.5 times. This is a big deal. This means that this algorithm can scale. So okay, so this is all very good and all for ordinary Euclidean spaces, but we know that phylogenies are actually a lot more complicated. We're really thinking about what the space of phylogenies is. We can sort of think of that in 2 components. One of them is all possible topologies, so we want to be looking at all possible topologies, and then for each topology we want to look at all possible branch lengths for that topology. So this is the sort of the entire space that we're looking at. And so we can take advantage of the fact that for a single topology, we know that the branch lengths form a Euclidean space. And we're good at Euclidean spaces. The Hamiltonian Monte Carlo algorithm works great for Euclidean spaces. So then all we need to do is we need to sort of figure out how we can move continuously between topologies in the space. So what do I mean by that? So we had some contention about what exactly this is called, but if you're familiar with VHV space, or sort of an NNI space with branches, this is what we're about to look at. So the idea is if you've got some tree looking like this, you can imagine sort of contracting this internal branch here, so you get sort of this degenerate tree with this polytomy here. And then you've got sort of 2 options for how to expand it out. And then you'll see, depending on how we expand it, we can get sort of these 2 neighboring NNI trees. So the idea is that we have a Euclidean space for the branch lengths here, and you've got a Euclidean space for the branch lengths here and here. So we can sort of imagine gluing together the space for here and here, based on the fact that you can get from this tree to this tree sort of continuously by making this branch go to 0 and then re-expanding it out. And you can get between, you know, this tree and this tree, or this tree and this tree in much the same way. So we're going to take advantage. This is sort of what a space is going to look like. We're just gluing together these different Euclidean spaces. And then so then we also need to introduce a leapfrog integrator. And the reason we're introducing this new integrator is because at each tree we have, when the branch length goes through, we've got a couple of choices. It's not clear where we want to go. So the leapfrog integrator is a probabilistic generalization of the leapfrog integrator. And so it's exactly like I said, when the branch length goes to 0, we're just going to choose randomly from the trees we have available. And I should emphasize that we're not just choosing from the 2 new trees we can go to, but we're also, with equal probability, just considering staying on the same tree we are and continuing to extend the branch length on the same tree. So what does that look like? So we can end up with something like this. So we can imagine sort of a path through the space. This is one tree, and this is a Euclidean space for that one tree. We can imagine, you know, moving through that one branch length goes to 0, then we can transition onto a new tree and then keep moving until maybe another branch length goes to 0, and then we move on to get another tree. And so sort of the choices we can see we're making is that when one branch length goes to 0, we have sort of a choice of 2 spaces to go to, or just remain on the whole space. So we could start here and end up here, 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 according to sort of these probabilities. So how does this look in practice? So to kind of make things simple, suppose we're just interested in inferring like an internal, we're just interested in this internal branch here we're not worried about. So we've got a 4 taxa tree and we just want to learn about that one branch. Then we end up with something that looks like this. So these are the sort of, each one of these represents sort of the curve, the posterior probability once it's been, you know, transformed according to our physics. So this is actually like a ski slope. And we can sort of see how the robot's moving on it. So this is for one topology in blue, another topology in red, another topology in green. We can actually see how the tree is changing as the robot's moving through this space. And this is our favorite, you know, humans, gorillas, orangutans, and chimps. And we can see actually, yeah, maximum likely positions here when we're on the tree that puts the chimps and the humans together. The important thing is you can see sort of where the trees connect in the middle, and that's where the transitions are happening. You can see sometimes it stays on the same one, and sometimes it moves to another one. And again, this is a fairly simple problem, so it's not very interesting because we're just inferring the single internal branch length. But obviously, this problem gets more complicated when you look at bigger trees and more parameters. So The really important thing, again, of course, is the acceptance probability. We want to know is we're taking lots and lots of these leapfrog steps. We're integrating our dynamics. We're simulating the motion of the robot through the space. We want to be sure that our energy is being conserved, and basically we want to be sure that we've got a high acceptance probability. So we want maybe something looking like this, where the acceptance probability is always like above 0.9, but we haven't proven that the integrator that gets these results is correct yet. Currently, the one we've shown to be correct is more like this. So it's not quite very nice. And again, this is a simple problem, so sometimes it still does okay, but a lot of times it's not doing so when we're getting sort of these low acceptance probabilities. And so why is it that it's so high? And the reason is because if we sort of zoom in on the place where the three different hills we have meet, we have this one point here, and this point is non-differentiable, which means it's not smooth up there. And so we're imagining sort of the robot going on the space. We really want it to be hugging close to the cliff here. It needs to be hugging it as it goes down on another one. We can't really have it, going off and doing tricks. And so we need to be very, very careful. And that's what makes the problem actually quite high. And so still have some work to do to try and come up with a good integrator that doesn't have trouble with this non-differentiability. I should emphasize this non-differentiability comes from both the prior and the likelihood. So it's continuous, but it's not differentiable. It's not smooth. So what I found on much, so the great thing we've done is we've generalized HMC to phylogenetic tree space. And we've got lots of good ideas for how to make an integrator that will have good performance, that will hug close to the cliff in sort of this non-differentiable point. And we've got an open source implementation. Please take a look at it. But sort of our current work is to try and prove that we've got to prove that one of these leapfrog integrators is correct. And then it would be great, I think, to see this extended to unrooted trees. So we've got rooted trees, and also a few ideas. There's all kinds of ways to extend HMC to make it even more efficient than what we already have. And so these slides at the link, DOI, and thanks to Alex and AWC for funding, Luigi for getting me here, and these are some references I mentioned.